Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for rest we are here to talk. So we were following our pattern wise DSA sheet. The topic was binary tree, basically binary search tree pattern, and we'll do the next question, which is validate binary search tree. So let's read the problem statement. The problem says that we will be given the root of the binary tree and we have to determine if it is a valid binary search tree or not. What is valid binary search tree? Basically, it says the left subtree of a node contains only one node with keys strictly less than the node's key. That's what the definition of binary search tree. Here is our binary search tree. For every node, like this node, this root should be greater than maximum of nodes of its left subtree. Okay, then we can say yes, 5 is correct. Similarly, A5 should be smaller than the minimum of all values of like from right subtree. Okay, so then only we can say yes, this node follows. Similarly, we have to check for this also. Similarly, we have to check, basically the rule should follow for each and every node. If we can check that, we have to return true. If the condition fails, we have to return false. So let's read the constraint. It says the minimum number of nodes will be 1. Okay, and the maximum number of nodes will be 10 power 4. Okay, so we have to look for basically linear code. I hope you know that why and how beyond 10 power 8 the code might give us TLE, and by seeing the constraint how to approach for the optimized ones. If no, then I will attach the link of the video, you can definitely check it out. And that's it. Also, the node value can go from minus 2 power 31 to 2 power 31 minus 1, which is the extreme limit of an integer value. We would have stored this in long if we have to play with the values, but here we do not have to play with the values. Play means modify. Modify means add multiplication or something, because these are already on their limits. So adding a single number can make it integer overflow, and hence in that situation we have to convert this into long format. But as here we just have to reach to the nodes and we just have to check the values if they are greater or smaller, so we do not need to modify, and hence it's safe. Okay, so basically we will start from 5. Can I say that? Now what is the condition? I'll say hey, make a call towards my left subtree. Okay, run in the entire tree and give me the maximum value. Okay, so I will run in the entire tree and I'll give the maximum v value, which is 6. Similarly, I'll make a call towards my right side and I will bring the minimum value. Okay, and as it is about minimum value, so definitely we have to keep moving towards the left side of that subtree. Can I say that? Because if I'll move towards right side, that will be storing the maximum number. That then it does not make sense on going towards right side. Can I say that? So basically I need maximum value from the left subtree. So keep moving towards the right side in the left subtree, so that we will get maximum value. Similarly, I need minimum value from the right subtree. So I'll keep running, like moving towards my left side. Okay, and once I found the maximum and minimum, so what will happen here? The maximum value will be 3, 6, 6, and now I'll say hey, 5 should be greater than the maximum value towards, like from the left subtree, and it is 6, which is not true. So hence here to in starting only we got to know that this is not a binary search tree. Okay. Now suppose here it was not 6 and here it was 2. Let's say 2. Now what will happen? We'll get the minimum value, which is 2, and we'll say hey, 5 is greater than 2, which is correct, and 5 should be smaller than the minimum value from the right side. Okay, so instead of running on the entire subtree to get the minimum value, what we followed, start from this root dot right node and just keep moving until it has left. So we'll find 6 is the minimum value. Now if you're thinking 2 is the minimum value, that is not the correct condition. When we'll reach at node 7, for 7 towards the right side, we'll get 2 minimum value. Okay, but for 5, if it was a correct binary search tree, then this would have not been 2. Okay, so we'll get minimum value from like here 7 and 6. So 6 is a minimum value and we'll fill this. So now we'll get to know hey, 5 is greater than 2 and lesser than 6. It means yes, this 5 is actually following the rule of binary search tree. Okay, now we'll move to the next node. Let's say 3. Okay, so we move to the 3 and we want to go towards the left side and want to get the maximum value, but as it is null, so it's already following the rule. Okay, now we'll move towards the right side and we'll get the minimum value, and we got 2. So the rule should be like this, it should greater than but it's not there, so null. Now if it is null, because we have to compare with the integer, so if it is null, just send 0. Okay, so if it is greater than 3, like 3 is greater than 0, yes, and 3 should be smaller than the minimum value from the right side, which is 2, and hence this is not following the rule. So 3 is not following the rule. So a single node, like any single node, if does not follow the rule of BST, we can say yes, the complete tree is not a BST. So return false then and there. So very simple. But in the worst case, what will happen? Because in this approach, we are actually iterating on every single node, like let's say this 5. And now we are making a call towards left side to get the maximum value, and we are moving towards the left side to get the minimum value, correct? To compare. So for every single node, what is the number of traversals we are doing? Can I say, because we are moving toward only right side, right side, right side, so number of levels, correct? So for every single node, O of log in towards left side, O of log in towards right side, correct? Correct? Every single node, log n, which is 2 log n. So don't you think this, like this is larger? Can we optimize this time complexity? If we have to optimize this time complexity in linear, what we have to do? So here at every node, we don't know what is the left value and right value. Then we are going towards it and then checking. If we have to make it O of n, it will be linear. Why? Because we cannot validate a binary search tree without checking every single node. And if we have to check every single node, the minimum time complexity it will take is O of n. Okay. So now we are at 5. So instead of checking towards downward, why not to check from the upside? Key, like check if till now everything is correct. So we'll check if 5 is correct. Yes. Okay. Because obviously root will be correct only. Now we'll go towards left side and right side. So what do you think? Towards the left side, which is 3. What is the limit for 3? Can I say that 3 can be anything but less than 5? Can I say that? 3 can be anything but less than 5. Similarly, 7 can be anything but greater than 5. Correct? If it is, then we can say yes, till now everything is correct. Very simple rule. So if we have to send something, some limit we can say, right? So for every root there should be some limit. Okay. So for 3 that should be maximum limit, which is 5. 3 should be lesser than 5. For 7, the minimum limit. It's not maximum, it's minimum limit. So can I say that for every node there should be some maximum limit and minimum limit, and every node should lie between that maximum and minimum limit. Did you understand? Let's say what we said. So we'll start from the root. So let's say we have a function, we have root and we have a max, let's say first minimum limit. We have a minimum limit and we have a maximum limit. That's it. Okay. Now for at first, this is my root. So the minimum and maximum limit should be true, should return true for the root also. So don't you think the minimum limit should be minus infinite and this should be plus infinite? So we can say yes, root lies. Yeah. And now when we'll move towards my left side, when we will move towards my left side, what I'll send? Root will be as it is, minimum limit will be as it is, but maximum limit will be the root value. Ki, hey, you can be anything but less than 5, which is maximum limit. Can I say? So towards my left side, I just have to change this max limit, and towards my right side, I just have to change this minimum limit. Correct? But let's say what will be the false condition, because if you are making the call left and right, correct? You can make call to left and right only when this actually returns true. Like when this is correct, and if this is correct, then only go towards left and right. If this is false, return false then and there. So what will be that false condition? So can I say ki if my root value is less than is equal to minimum value and not, or if anything returns false, or if root is greater than equal to max value. So this is the outer limit. Ki root cannot be, what I said, ki root cannot be equal to 5 also. Root should be, like this 3 should be what? Less than 5. So if I'm saying 3 is greater than 5, which is max limit, and similarly root, minimum limit. So if root is less than, this is my minimum limit, this is my maximum limit. So if my root lies between this, it is correct. So I am checking if my root lies this side or my root lies this side. This is what I am checking. If my root less than minimum or root greater than maximum, then I can say return false. Correct? So return false. If it is no, initially 5, from it does not lies beyond minus infinite or beyond plus infinite. It lies in between. So for sure this if case will not run, and for this we have to go towards left side and we have to go towards right side. Okay. Can you see that? Now I'll go towards left side and now I'll go towards right side. So what if left side returns everything true, but if for any single node the right subtree has given me false, so what should be the final answer? False, correct? So this and this or this or this. If you will write true like this or this, so if this returns true and this returns false also, the final answer will be true, correct? Because or returns any single true. So hence between the left call and right call we have to put a AND operator sign. So very simple. I will return by calling the function, let's say function. Now I'll go towards my left side. When I'm going towards my left side, minimum will be as it is, but maximum will be root dot value. With AND sign, I'll call the next function. I'll go towards my right side. Now here minimum will change. Minimum will be root dot value and maximum will be as it is. Okay. So let's see what will happen. Initially 5. So I will be making this sign over here. Okay. Let's say minus infinite to plus infinite. Now I'll go towards this side, minus infinite to 5. Does this 3 lies in between this? Yes. Now I'll go towards left, but see, listen it very carefully. Because the return type is boolean, so when my root is null, what should I return? Should I return false ki hey, this does not follow BST condition, or should I return true? Because to return false, the condition should, fail, right? But when my root does not exist, I cannot say ki false, correct? So hence, if my root null, return true. So if my root is null, return true. Okay. So now for this side, it will return true. Now we'll go towards 2. So when we'll go towards 2, see, listen it very carefully. When we are going towards right side, so minimum will change with 3. Okay. So minimum will change with 3, but maximum will be whatever the parent's maximum, which is 5. Don't think it will be plus infinite. It will be parent's maximum. Okay. So parent's maximum is 5, so we'll send 5. Now we'll check, is my 2 lies in between this? I'll check, hey, is my 2 is less than 3 or greater than 5 to make it false? Yes, 2 is less than. So it will return false then and there. So this side will return false. And as it was true and false, so it will return false. So for 5, the left call only returned false. So because this is an AND operator, so we'll not go for the right check. Okay, so we'll return false from then and there. This is the condition. Okay. Now let's say it was 4. Let's check another condition also. So this will be 3 to 5 only. And now as the 4 lies between 3 to 5, so obviously it will return true. Okay, so it will return true. Now for 3, left side is also true, right side is also true, so it will return true. So for 5, left side is true. Now we'll go towards right side, which is 7. So when we'll go towards right side, which is 7, the minimum value will be 5, the maximum value will be infinity. Correct? Now 7 lies between 5 to infinite? Yes. Now we'll go towards left side, which is 6. So when we are going towards the left side, the minimum will remain same, which is 5, but maximum will change, which is 7. And as 6 lies between 5 and 7, so it is correct. So hence this will also return true. Now we'll go towards right side. Basically, we have to go towards this side also null. And when it is null, so this will also return true, this will also return true, and both together with AND operator, this will return true. I hope you get it. Now we'll go towards right side, and as we are going towards right side, so definitely the minimum will change, which is 7 to infinite. And as 8 lies between 7 to infinite, so it is correct. Now we'll go towards left side. Similarly, 7 will be as it is, but 8. Now we'll check, is my 2 lies between 7 and 8? No. So this is a false. So now this will return false. Now as this left side has returned false, so for 8 will not go towards right side and will return false then and there. So for 7, left side is true, right side is false. So because of this AND operator, 7 will return false. Now for 5, left side has returned true and right side has returned false. So with the AND operator, total become false. So hence at the end we can say this is not a binary search tree. Hence we have validated it. So the time complexity, we are actually going on every node. It's not about every level. Okay. So hence now the time complexity has been reduced from O of n square or n log n to O of n. Why? Because instead of checking towards downward the condition is true or not, we are checking from upward only the condition is true or not. Okay. So in the worst case, you will here, when did we get to know ki this is false condition? When we reached that last node, you can say second last node, which is nothing but O of n time complexity. And what about the space complexity? Space will be definitely O of n only. Why? Because the number of calls we have made for every node. So hence the space complexity will be O of n. So let's write the code in the editor. So here is the code what we have discussed. Here we'll call the DFS function here, and if my root is null, return true, and if the condition fails, means if my root value goes beyond minimum value or maximum value, then we will return false, or else we have to do the similar check for the left side and right side. Okay, now here if you are saying ki minimum and maximum value, so we have considered a long min and max, then why not int min and max? We could have, but as you can see here the question says ki the node value can go up to that 2 power 31 minus 1, and if you know that is the maximum limit. Okay, and as we are checking ki if my root value is equal to, less than equal to, so equal to is also there. So if we'll put that integer max and min value, then in such case it might become yes, both are equal, and either it is true, it will consider them in the false condition. Okay, so that is the reason ki if it, let's say if it says ki the maximum number of limits can be till 10. Okay, so basically we have to put 11 na to check ki till 10 it is correct or not. So if we'll put 11, then here if we'll put 2 power 31 minus 1 plus 1, it will go beyond integer limit, correct? So hence that is the reason we are actually putting long, min and max value, and that's it. Let's run the code and let's submit this. Okay, so this was your linear code. So I hope you understood ki how this code was optimized compared to n log n code. Okay, so this is the code in Java, here is the code in C++, and here is the code in Python if you are from Python background. So I hope you have actually understood and you will submit on your own, along with you are also making your own notes. That's it. Let's mark the next question as done, and that's it for this video. Let's meet in another video. If you have any doubt, let me know in the comment section, and if you really like the video, please do hit the like button, because that gives me more motivation to make more videos for you all. I'll attach the sheet link and my social media links. If you have any doubt or if you need any guidance, you can definitely reach out to me, and you can even share your progress on social media by tagging Rising Brain and my profile as well. That's it. Let's meet in another video. Till then, keep learning, take care of yourself and your family too.